Okay, so first of all, I'd like to apologize for everyone that we have been delayed this lecture for several weeks due to various reasons. And I'm very happy that we resume this lecture today. So my name is Lei Xiao. I'm one of the organizers for Cadasa. So today's lecture, we're gonna develop in two parts. So the first part will be led by myself. I will introduce my understanding of BERT and also what kind of journey that I have gone through to understand BERT. And the second part will be a more detailed technical discussion led by Dr. Daniel Mao. He's finally a doctor now. Congrats. And if you have any questions, feel free to interrupt or throw your questions in the chat box. All right, so my topic today is basically to discuss about how I form my own understanding of BERT purely from the historical view of pre-trained language models. Just because I am not a researcher or haven't worked in NLP at all, so it took me a while to understand what is BERT, even though there are a lot of buzzwords about BERT in the internet. But it took me a while to wrap my head around and start understanding BERT. So if you Google BERT, like I have done several times, you will be overwhelmed by a lot of information here. So you can see here we have about 1.4 billion results. And I don't know, maybe BERT is a product is created by Google. So obviously the original paper was showing up first, which is good. So when I Googling BERT, my first my first impression was like, wow, there are so many information, and I have heard it from a lot of media and friends, and also even in our Kadasa's WeChat group, we have people posted about BERT. It almost like a magic tool for me. So, however, when I look at it, where should I start? I look into Wikipedia and also some blog posts, and even I started reading the original paper. But to be honest, I didn't understand most of those content based on the results that I found on Google, at least from my initial first or second trials. So it's very overwhelming for myself to understand. And as I said, I'm not a NLP practitioner or researcher. So when I look at the BERT model for the first time, so I read the name Bi-Directional Encoder representation from Transformers. I can only understand the first word, bidirectional, but it's probably not the same thing that I understand in a language from a language modeling perspective. And when I saw this word transformers, I was like, what is transformer? So just by looking at this name, I have a lot of questions arrived already, and I don't know. I have no idea where should I start. Should I start looking for what does a transformer mean in NLP, and also what is encoder representations? So basically, I have so many questions, and I don't know where to start. And even I look at some blog posts, either it's towards data science or Quora, and there are so many things, and most of them have some technical discussions, and those technical discussions usually require pre-understanding of, for example, what is transformer, and also some of other contextual representations. So I struggled my head around a lot, and I started thinking, there must be a reason that everybody loves BERT, because when you look at the results, it seems like BERT has beaten most of the other models. So I continued digging into more and more details. Then I find some really interesting hints from the original paper. So what does this original paper tell us? If you just look at the title, it mentioned about pre-training. Of course, there are some other words such as bidirectional transformers, which I have 1,000 question marks. I don't understand what they are, but I do understand pre-training because based on my experience in other areas like the computer vision, I have heard about these words before. And then I dig into more details. I start looking at the appendix of this original paper. When I look at Appendix A, there are some additional details. So if you look at the Appendix A, like they have 5 sections talking about, what the illustration of pre-training tasks and what are the pre-training procedures and fine-tuning procedure. So they're basically talking about pre-training. And then that's when I realized that maybe this paper has a lot to do with pre-training. So I started Googling pre-training in NLP, and I found both in English and Chinese, and I found some awesome blog posts. So one post is from Zhihu, which talk about pre-training in NLP, and they also talk about the like the meaning of BERT in that perspective, and also read some other articles that kind of focus on explaining pre-training in NLP. And I started understanding more about BERT, just from the pre-training perspective. And for the Appendix B and C, and I really don't understand, or I really don't care, because I am not a NLP researcher, so I probably will not have additional training or works in those areas. But I do want to understand how pre-training works. So as I said, I have, I know about pre-training in computer vision. So basically, a lot of deep neural networks, they're trained on large data sets such as ImageNet, and they have that hierarchical feature representations in different layers. And so basically, for a very good deep neural network, either it is the ResNet or some other architectures. So for their first several layers, they can learn some general features that can be almost applied to any specific projects. So that's the true meaningful reason that why we want to use pre-training, because we want to have those pre-trained features ready and for our fine-tuning projects. And this is something that I can understand. And the same thing here, pre-training is just when we have a smaller data set, we basically freeze our pre-trained parameters, or we'll have them as our initialization for the further fine-tuning processes. However, this can be really useful, which means that we don't have to train all the models that we have. So I think this idea will also apply to our language models, and that's exactly what I find. So basically, and also we have learned from this course that language models are the backbone of NLP practices and researches. So then, as I said, I found some really awesome blogs talking about pre-training in NLP. And that's how I started linking different topics together. And all the way led me to understand BERT. So first of all, we all have learned word embedding in this course, and including the word to VAC and glove models. So basically, these word embeddings are the basis of deep learning for NLP, as Jacob mentioned here. So, so, so this also like all these were embeddings. If you trying to think about um, like if we compare them um, to computer vision, we can somehow treat them as a very I would say the very first pre-trained model in NLP. Um, so so the word to VAC, you can see that they have like two. Um, uh, they have the uh, continuous bag of words and also the skip gram, and so basically they can learn from they can train from the large set of corpus and trying to find relationships between different word vectors, and those word embeddings are basically the pre-trained form that we can use in our other tasks. So here you can, well, this is the picture that I copied from the blog post that I read. So basically, if you were doing a question Q&A task, and we have this architecture here, and so the word embedding or the word vectors for each word actually can be seen as a initialization of our network, and we can either freeze them or do some further fine tuning to update that word embedding. So this is the very first form of pre-training in NLP, which is word embedding. Then there are some setbacks, or there are some limitations in the word back. The biggest challenge is that it can't deal with multiple contexts. If you see the example here, so bank can have two different meanings in different contexts. So because you can either understand it as a bank of a river, or it's a bank that we usually go to and withdraw money. So however, in the word to VAC world, the word embeddings are applied in a context-free manner. So either you're opening a bank account or you're working on a river bank, the word embedding in the word to VAC or globe word will have the same embeddings. So this will cause a lot of problems, because basically we can't deal with multiple contexts by using that method. Therefore, the Elmo was created, and so they started, the researchers in this field started thinking about maybe we should focus more on training contextual representations. So basically, for the same word, if it is in a different sentence or different context, they should have a different embeddings and different embeddings. So that's the shift towards the contextual representation, which in the second part that Daniel will present, he'll present more technical details in this contextual representations. Here's a kind of architecture that Elmo used. So Elmo is created by researchers from University of Washington. So it's actually it's called deep contextual word embeddings. So it used a bi-directional method. So it's training the sentence from either left to right and right to left. And they used the LSTM, which is recurrent neural network that we learned, I think, in previous lecture. So it's basically using this LSTM to train the language model on a bi-directional. So it is not predicting, it is using the context before and context after to train the model on two directions. So it can capture the context much better than the previous word to vec method. And as you can see here that, so basically when we input, so the words are input as a word embedding. So we have a word vector. And on the second and third layer, we have, they both use LSTM layer, but they have two different directions. So therefore you have a second intermediate word vector generated by the first LSTM layer. Then the second LSTM layer will generate a third intermediate word vector. So the final representation of this model will be a weighted sum of these three embeddings. And in the next phase, when you're trying to use this model, so basically you're training your features on your specific task by finding appropriate weighting for these three embeddings. And also there is another advancement in the contextual representation area, which is proposed by OpenAI's generative pre-training. So they published this paper in 2018. And so what they have done differently from Elmo was that they choose transformer instead of LSTM in their modeling process. However, they only use one direction, so they didn't so it's a unidirection. They didn't use a bi-directional approach, but because they use the transformer, which is much more powerful modeling technique than LSTM in NLP. So they have trained this on a very large data set, so they have obtained a very good result. So we have a pretty good understanding of the historical development of pre-trained language models, and you can tell that word embedding, the very initial work introduced by the word to vec, kind of gave us some ideas, some framework of how this pre-training idea might work. Then Elmo and OpenAI's GPT kind of improved by using different architecture such as bi-directional training and also using transformer, somehow solved our multiple context challenges. So for a single word, even though you might have different meanings, right now we can capture that context very well. So BERT show up, BERT emerged by, I would say, from the historical point of view, it basically stood on the shoulders of giants. Because when you look at the original paper about BERT, they have compared their architecture with OpenAI's GPT and also Elmo. And so they also, they also claim by themselves that the difference in pre-training model architectures are that BERT uses bidirectional transformer. And all the rest, they use bidirectional, but so basically the BERT use bidirectional and also use transformer. So this is the only difference between these three models. Plus, BERT has, in that original paper, BERT also introduced some other techniques we'll introduce later, such as mask language model and also next sentence representation. So if we conceptually, if we can do some plus or minus thing, so this is our BERT. And this is OpenAI's GPT. So OpenAI also use transformer, same thing in BERT. The only difference was that OpenAI, the major difference is OpenAI used a unidirectional structure. So there's no bidirectional. However, in BERT, it's bidirectional. And if you compare BERT with Elmo, they're pretty much the same, except BERT used transformer instead of LSTM. And I think some of the innovative ideas proposed by the BERT paper was that it proposed this masked LM method and also the next sentence prediction method. So it's basically the same idea from word to vec Sable. So it'll mask a words, it's a random words, and use all the other words to predict that. But BERT does a very, very good job by going more details in how you want to mask your local word, and also because it is also trying to solve in the problem of sentences. So it introduced the next sentence prediction to its training process, which make it much more powerful than the word to vec. So when we know from a high level, we understand that BERT has two major differences from other method. So I would say the most important improvement, or I would say backbone in BERT was the utilized transformer, and transformer wasn't first introduced in BERT. It was introduced by the paper called "Attention is All You Need," and OpenAI GPT also used that architecture. So basically, transformer is a much more powerful modeling technique than LSTM, which I will leave Daniel to explain more in his second part about transformer. The second thing that BERT utilized was a bidirectional model. So as we have seen in Elmo model was that it is looking from both directions, from left to right and right to left. So therefore, in it is masking tasks. It can mask any word in a sentence without considering about directions. So as I mentioned previously, masked LM was another contribution of the BERT original paper. So what they used was they always mask about 50% of their whole data set, and they mask them randomly. So they mask this word and replace with a mask encoder and use the model to try to predict the real word, and so that they can train the model with a lot of, so basically you don't have to manually label your data set, which make it into a unsupervised learning process. And in their paper, they discussed about, they don't want too much masking nor too little masking, either from a computational perspective, and also they want to learn learn the context the most from their data set. So what did they do actually is, when they're masking, so here as I said, they masked 15% of the words. However, in their masked words, they didn't mask 100% of them. So they choose to replace those ones with mask sorry, any questions? Okay. So they only masked 80%. What they did is they left 10% of those with a random word. So they just replaced that real word with a random word from whole corpus. They also did choose to keep the same of the word in another 10%. So basically, they told they said, oh, they wanted to mask, but they actually didn't mask that word. So they didn't do anything. That's in that way they will reserve that 10% of the words. Another important innovation they introduced was the next sentence prediction. So I think in BERT, if I remember correctly, so for every training sample, they have 2 sentences. So in addition to learning the language model for each word, they're also trying to find the relationship between the 2 sentences. So basically, they're trying to say my second sentence B, if whether that sentence B is right after my sentence A. So basically, they're trying to learn the relationship between, or the contextual relationship between 2 different sentences. And so because of these considerations in their input parameters, they have a very unique structure. So if you look at the input representations, you can see that they have position embedding. So in this embedding, each word have its own position. They also have a segment embedding. As I said, that they have 2 different sentences. They want to embed each word to see whether that word is in sentence A or B. They also have a token embedding. So basically, these 3 embeddings are in the BERT model that they're going to learn. And the fine tune, because BERT is so powerful, it had first of all, it used bidirectional learning, and also it used transformers. And plus, they have considered the next sentence prediction. Therefore, the BERT pre-trained model, language model can be literally applied to any language challenges. So they can utilize this the pre-trained model to fine-tuning on different tasks, such as the question and answering tasks, and also some of the sentiment analysis tasks. So they only need to fine-tune this model with their own specific data set, and usually they'll obtain very good results. I think that's pretty much my part of presentation. So basically, I have introduced my understanding of BERT from a historical perspective, how pre-trained model is progressing in NLP. And I find it is very helpful for me to connect all all the dots in NLP modeling journey. So basically, especially when I try to compare the difference from BERT to our fundamental word embedding technique, such as BERT to VAC, it really helped me to understand what BERT has done and how it stands on the shoulders of giants. So for further ratings for us will be, there are some post-BERT training. So the first 4 are basically papers that are developed on top of BERT, so they have improved on BERT, trying to get better results. The last one is an improvement on OpenAI's GPT. As you have already heard about GPT-3, it's the company didn't open source it just because it's too powerful to be given to the hands of wrong people. So that's why they only offered API access. However, this model has trained on, I believe it's 17 billion parameters, and it's pretty much it's the closest thing that to the generative AI. So this paper is very interesting to read. So I'll leave it here, and hope you guys can find a lot of values from these papers. And if you have any questions, feel free to jump in. And that's my end of my presentation. I'll hand it over to Daniel.
All right. Thank you, Ray. So now I'm going to share my screen here. Let's see. Is my screen?
Yeah, we can see.
Okay, sure. So thank you, Ray. And also once again, apology for actually delaying or postponing the lecture by several weeks due to all different kind of reasons. But now we are back on it, and so Ray already gave us like a general introduction of BERT and some kind of historical development and how BERT was motivated and also developed. So I'm gonna actually jump in and introduce some kind of like vanilla technical details of this kind of model right here. So just pay attention here. This is like naive or really basic technical theories of BERT. It's not like comprehensive introduction of the BERT models right here. The goal of this lecture is try to get you understand the theoretical framework or the foundation of the BERT. So if you have really deep detailed like technical questions, here's a bunch of like different resource links you can get to actually understand a little bit more about the model. So the lecture actually going to be based on link 1 to 4. And the main lecture, like the main framework or the outline, going to be like link 1 and 2. 3 and 4 are more like the complementary or supplementary kind of reading for the basic like technical theories of the BERT. Meanwhile, when we are actually going through those 2 links right here. And there are some other additional really useful kind of resources as well. So the first one is by Toronto, like probably one of the most like famous AI or machine learning meeting group or study group, which is called AISC. They actually have the lecture, which is about 1 hour and 15 minutes on BERT. So if you're interested, you can just take a look up this video right here. And another link is the original paper. This paper is actually it covers actually 100% of the model because that's the original paper. Is like especially the training process and how the mask and also the sentence comparison tasks are actually implemented in this kind of model right here. and a visual guide of using BERT. This is more like a empirical details how to actually run this kind of model using TensorFlow in Google. Some kind of codes are included right here. If you are interested, you can just take a look as well. I think we got a question here. Let's see. Can you guys see the documents I'm sharing? I actually post a link to the chat box over there. And also in the WeChat group. Okay. All right, so let's get started from the first part. So like Ray just mentioned, like BERT stands for Bi-Directional Encoder Representation from Transformers. So since it's kind of like model based on transformers, so the first part of my lecture will be some kind of detailed, although a vanilla explanation of transformers. So I'm actually going to use this post right here, which is first link illustrated transformer, to tell you guys, a full look of what a transformer is. Then we are going to move on from that to the BERT, because the BERT is actually a special type of transformer over there. Okay, so what is a transformer? So transformer, basically, most of the transformers are actually used as a language model or translation model. Basically, you just input a sentence or sequence of the words in a specific language, and the transformer going to translate that into another language, which is the target language over there. So in the transformer, we have two main framework, or the submodels right here, encoder and decoder. So basically, you put the input sequence or the sentence you want to translate to into the encoder. It's going to be encoded as a contextual word representation. Then that's going to be passed to the decoder, and decoder is going to actually decompose that and translate that, or actually do, which I will talk about later, do some kind of attention.
Daniel?
Yeah.
I think we are all only seeing the desktop. Can you please check the share screen sharing?
Oh, the screen. Okay, sure.
Thank you.
Can you guys see right now?
Yeah, that works.
Okay, let's go back to this. So what is a transformer? The transformer actually was proposed in the paper Attention is All You Need. I think the lecture, like in CS 224, the author of this paper has been invited to give a lecture. I think there's some questions over there. Okay, to give some kind of like a lecture, guest lecture in this kind of course. If you're interested in, you can just take a look over there. So it is actually mainly used for language translation. So the full look or high level look will just be like this. So the transformer is like some kind of black box. You input some kind of language or sentence or sequence of the words you want to translate. It's going to give you the sentence of the words that you in the target language over there. So a little bit more detailed look of this model. It has two parts. First part is encoder, second part is decoder, just like the sequence model. But later on, I'll show you the difference. Well, sequence model is like a single encoder to a single decoder. But for a transformer, it's a bunch of different encoders and a bunch of different decoders. Okay. So basically, you put a sentence you want to translate to into the encoder. It got you the contextual words representation. Then it's going to pass it to the decoder, and decoder going to decompose that into another language of sequence over there. Okay. So yeah, this is what I mentioned here. So the encoding component is actually a stack of encoders. Here we have 6, but usually, in some complicated models, we could have more. So these decoder also have 6 different decoders right here. So if you have 6 encoder, you have to have 6 decoders, because once every single encoder, which I'll talk about later, will be mapped to one of the decoders for further process. Okay, so yeah, just like I mentioned here, the decoding component is a stack of decoders of same number, just as encoders. Okay, so let's actually dig a little bit more into the encoder and see what's inside the encoder here. So the encoder are all individual in structure, and each of them actually have two components. One is one layer, or I would say not, yeah, technically it's not layer. It's more like its own kind of like network. So it's self-attention. And once you finish that self-attention, then you're going to pass the output of self-attention to the forward for the neural network, which is just like a normal artificial neural network we have. And it's going to generate another output. And that output is going to be passed to the next encoder. So basically, it's a next encoder, nested encoder. So basically, you encode one layer, then next to another layer, encode again, encode again, encode again. So it's kind of wrapped one by one layer, wrapped by second layer, so on and so forth. Okay. So yeah, so each kind of encoder is broken into two sublayers. Those two sublayers. Now, that's the encoder's input first flow, just like I mentioned, through a self-attention layer. So what is the self-attention layer? It's a layer that helps the encoder to look at other words in the input sentence as it encodes the specific words. It sounds a little bit abstract, but later on, I'll show you the detailed explanation how the self-attention works. But just take my words right now. So this is a layer that helps the encoder words actually try to find a relation between this kind of word and other words. So more generally speaking, self-attention try to look at the relationship between the specific words and other words. For example, if we suppose, let me try this, okay. Suppose the sentence I wanna translate is, I want to go out, okay. Then you can just name one of the words. Suppose want is a word I wanna actually use for self-attention. Then what self-attention does is it's gonna find out the relationship between one and I, between one and itself, between one and two, between one and go, between one and out. Basically, try to figure out the relative position semantically, or the relative semantic position of one or specific word in the sentence over there. Okay, and how that works. That's the self-attention here. Okay, so let's go back to the model. So for the decoder has pretty much a very similar structure as the encoder. It has self-attention. It also has the feed-forward neural network. But between the two layers, we also have the encoder-decoder attention. So I think we actually mentioned this in sequence to sequence. When we do the language model, when we do the translation, we need to think about the targeted word, how the targeted word is going to focus on the specific original word. So for example, I think we had this example previously. Let's try this. Again, let's use this as example. I want to go out. Suppose, so that's English. That's English word, the original sentence I want to actually translate. And suppose, another language we want to translate is Chinese. 我想出去. Okay, so the encoder-decoder attention is more like try to link every single word in the decoder to every single word in the encoder. That is, when I actually want to translate I, or want to actually get a word 我, how much relationship or how similar 我 is to I, to want, to go, to out. Okay, so it's more like a relationship between the targeted word or target sentence to the input sentence over there. Okay, but self-attention is actually within the original sentence and try to find the inner relationship between each single word and another word. For the encoder-decoder, is between this encoder, between the original language and the translated language over there. Okay, so that's the difference between the two. I won't actually spend too much time on the encoder and decoder attention because we actually talked about that in the sequence model, but I'm going to spend a little bit of time on self-attention, try to explain what it is later. Okay. So now let's actually break the technical details a little bit more inside the encoder, because encoder and decoder are pretty much the same. So I'm gonna actually spend a little bit more time on the encoder. Then the decoder is actually just one more layer on top of the encoder in the middle. So let's think about a sentence that we try to translate, which is French. So the French sentence is je suis étudiant. So that means I am a student. Okay. So suppose those are three words we want to translate into English. Je is the first word, and suis is the second word, and étudiant is the third word over here. Okay. So we have three different words. So the first step is actually translate or convert each kind of word into word embedding. So in this kind of example, each word is embedded into vector size 512. So it doesn't look like 512 because we can't, make it that long. So I will just pretend this four kind of cell, like the length of this is 512. So that's the first step. We have to use some kind of word embedding to represent a word. You can create a word embedding yourself, or you can use some pre-trained word embedding. Okay. So once we have the word embedding, we are going to feed that into the self-attention layer. Okay. So the embedding only happens in the bottommost encoder. So that means we only use the input sentence right here. And later on, we don't pass that into the second encoder. We only pass that to the bottom left encoder. And the output of that encoder is going to be the input of the next encoder. Okay. So that's the first stuff I want to actually stress out a little bit. And the abstraction that is common to all the encoder is that they receive a list of vectors, each of size 512, just like the embedding size. In the bottom encoder, that would be the word embedding. But in other encoders, just like I mentioned, it would be the output of the encoder that's directly below. Okay. The size of the list is actually the hyperparameter we can set. So basically, it would be the length of longest sentence in the training data set. Okay. So basically, if you want to actually input a word, a sentence of the word or the sequence, you have to find the longest sentence to accommodate all the possible sentences over there. And for the short sentence, which is less which is a little bit shorter than longest sentence, you have to use the padding to pad it with 0 so that you can actually make all the sentences equal and feed to the encoder here. So after embedding the word in the input sequence, each of them is actually going to flow through the two layers. So suppose je suis étudiant is going to be put into self-attention separately into 3 words and generate 3 different output, and it's going to put it into the forward feed neural network. Then it's going to be generated as output again, put into the next encoder. Okay. So the next part is let's go a little bit more details into the self-attention. Okay. So that's actually break the encoder and break them into the self-attention, look at how self-attention works. So before that, I just want to mention one more kind of detail right here. So as we mentioned already, so the encoder is going to receive a list or different embeddings or word vectors as input. Then it's going to process this kind of list by passing those kind of word embeddings into a self-attention layer, which we'll talk about later, forward neural network. But the thing is, each kind of word here has their kind of own feed-forward neural network. So this specific word will be passed to this feed-forward neural network and be generated as output over there. So those two are kind of separated from each other. Okay. Okay. So what is self-attention? So self-attention is really kind of similar to the encoder-decoder attention we talked about previously. So let's think about specific examples right here. Think about this example. The animal didn't cross the street because it was too weird. So if you look at the sentence, one of the concern I could have is 8 here for the machine to understand. So if you ask a machine or if you ask the language model, what is 8 here? It could be the animal, it could be a street. But according to us, like human, or using our brain, we can easily understand 8 is actually it's actually not the street. It's actually the animal, because it said it was too tired, so it should be the animal, not the street right here. But for the algorithm, it can't actually figure out which kind of word 8 refers to. So that's why we need attention. We need attention to link 8 to a specific word in the sentence. That's why I'm saying self-attention is more like within the sentence, we try to find a relationship between each pairwise kind of like words over there. Okay, so this is actually a final result of attention, like a well-defined self-attention layer. So as you can see here, 8 is the target word we want to link to other word. And those are just a bunch of like other word in the sentence over here. And the darker the color, the more linkage, or the more similar or more kind of like a larger relationship is going to have between the word 8 and that specific word. As you can see, animal and those two words are very, very close to 8. So the model then understand 8 as animal instead of like as street over here. And how does that work? So let's look into the details of self-attention right here. So a first step in calculating self-attention is actually create 3 vectors from each of the encoder's input vectors. So the 3 vectors are queries, or query vector, key vector, and a value vector. Okay, so 3 vectors, again, query vector, key vector, and value vector. These vectors are actually created by multiplying the embedding by the specific trained weights. Okay, so those are weights already trained during the encoding and decoding process. Those are just like the weights we already we initially just randomly put some kind of weights over there, but after the training, it's going to give us the best kind of weight we're going to use to generate a query, key, and a value vectors over here. The specific details on how to train the word, the weights right here, you can go back to the original paper. I won't spend too much time on that, but just take my words. Those are just trained weights we use it to actually. Just not take that as 512. Think about this is 101 times 4 vector, and this is going to be 4 times 3 vector. Okay, so 1 times 4, 4 times 3 is going to be 1 by 3 vector. Okay, so that's basically how you generate the 3 different vectors over here. And what do we use those vector for? Okay, so that is, what are the query, key, and value vectors? So they're basically abstractions that are very useful for calculating and thinking about self-aware attention right here. So once you actually understand how attention is calculated, like using this bunch of like weights right here, you will know pretty much how we need to know, why we actually need 3 vectors. Okay, so that's try to answer that question by looking, by actually going a little bit further, understanding the calculation process of the self-attention. So we finish our first step, we get 3 vectors. The second step is going to calculate the self-attention, and by using a score, which will be calculated later. Okay, so see, we are calculating self-attention for the first word, which is thinking. Okay, suppose this is input. In thinking machines are just 2 different words at the input sentence right here. We try to think about calculating self-attention score of thinking. So how we do? So we need to score each kind of word of the input relative to thinking. That is, we need to think about how thinking is, how thinking is relatively, like the position of the thinking relatively to other words in the sentence over here. So the score actually determines how much focus we want to place on other parts of the input sentence as we encode a word in the third position. That is, when we think about when you think about 8 right here, just like the original example, how much focus we want to put on other words. When we try to encode 8, how much focus we want to put on our animal on street. Obviously, when we encode 8, we want to put more focus on animal and not the street. So Similar kind of thinking can apply right here. When we encode thinking, we need to think about how thinking is, how much focus we should put on machine or other kind of words relative to thinking right here. Okay, so the score is actually calculated by the dot product of the query vector and key vector. So basically, you multiply the query vector and the key vector, so you get a score. So that's the second step. So this step again tells you how much focus you want to place on other words. So basically, you multiply the query from thinking to its own key vector, and you multiply the query from thinking to another key of different word, which is machine. Okay, so those two is going to tell you which word should we focus a little bit more. Of course, we should focus a little bit more on itself thinking, right? Because you multiply itself with its own key, so it should be like mostly correlated with itself. Okay, so the next step, or the third and fourth steps, I actually try to divide the score by 8. This is a conventional number used by the paper, but there's no actually limitation on what number you should use to actually normalize the score. But the author, actually Jacobs, actually used the 8 here. Okay, so how do you actually use the 8? It's actually from the square root of dimension with the key vector using the paper 64. But do we have to use 8? It doesn't have to be. The author said you can use other kind of like numbers over there, as long as the result actually got is pretty much, it's very pretty, or it actually makes sense. This number doesn't really matter that much. But the author used the 8 to try to normalize the score here. Okay, once you get the score, and normalized by 8, then you are going to pass the score to the softmax function. Okay, since the softmax function is going to give you the possibility of each single outcome over there. So the softmax function can normalize the score, so they're all positive and add up to 1. So it's going to give you a weight or the possibility that or a proportion of the focus that you should put on each kind of word over there. And 80% of the focus should be on thinking, and 12% of the thinking, like 12% of the focus should be on the machine over here. Okay, so basically that's how we actually generate the final outcome using softmax score. But that's actually not the end of the story. We have 2 more steps to go. The next step is actually multiply each value vector, multiply each kind of value vector here by the softmax score. The intuition here is actually try to keep those kind of value intact, and that we want to focus on, and drown out the irrelevant words. So this value here represents thinking. So that basically is a weighted average. Think about this. As this is the weight, and that's the word itself. You try to multiply the word with the weight. So, and later on in the next step, we're going to sum up the weighted value vectors. We're going to sum up 14 times, V1 times 0.88 plus V2 times 0.112. So basically, you can sum out the weighted average of each kind of word. You try to give them each single word a weight, and you're going to compress that into another vector, which is data here. Okay, so basically, the weighted average is going to tell you how much weight, how much focus I should put on each single word over there. Okay. So yeah, so last step is going to be just like I said, it's going to sum up the weighted vector value vectors. The procedure, this is going to produce the output of the self-attention layer at this position here. So basically, this is the final output here. So once you actually sum them up, so basically this kind of vector is going to tell you I actually should put much more kind of focus on thinking itself instead of the machines right here. So basically, it tells you which word you should focus on when you actually encode the specific word thinking right here. Okay, I want to pause here for a second in case any questions you have. Any question with the self-attention right here?
Yeah, I have a little question.
Sure, yeah.
So I'm just wondering, like, for the we already have self-attention, and it's is getting the relationship between this word and the other words in the sentence, and I know that transformer is also like using the positional embeddings. So although even we already have this self-attention, and so why are we still gonna have using this I mean positional embeddings?
Good question. So positional embeddings are actually trying to tell you the order of the word. It tries to tell you the sequence of the word. So suppose for example, for this sentence right here, the positional embedding basically tells you animal should be after Z and didn't should be after animal. But self-attention does a totally different job. It actually tells you when we try to encode animal, how much focus should we link, or should we focus, how much focus should we put on other words over there? Or when we actually try to encode 8, how much focus should we actually put on other words? So basically self-attention tells us the relationship between every other word and this word you are encoding. But the positional embedding is from a sequence perspective or sentence perspective. It tells you how the word should be ordered. Okay, so one is order, one is a relationship. So those are just two different kind of perspectives.
All right, thanks, Daniel. That makes sense.
Yeah, no problem.
So Daniel, how does it learn relationships between different words?
Okay, it basically learns that through the weighted average right here. So basically the value is represent the word thinking. Once you multiply the value by the weight, 0.88 plus, you know, the relative or, you know, the value of, where is that one? Oh, yes, by the weight 0.12 times this kind of value by weight 2, it's gonna tell the specific encoding of thinking that we should put 80% of focus on the thinking word itself and only 12% on other word over here. Okay, so basically the weighted average is some kind of way to tell you which word should we actually focus a little bit more and which word should we focus a little bit less.
So that's when it's learning the relationship on thinking, right?
Yes, on thinking. And you did the same for machine. And
Okay.
you do the same for every single word over there. Yes.
Okay, thank you.
Yeah. All right, any other questions? Okay, that's self-attention. All right, let's move to the next part. So basically, yeah, that's the matrix calculation. I would just, if you are interested, you can just look into the matrix calculation of self-attention, but I will just jump over this part because we already introduced that part, you know, graphically using this graph right here, because this is more like a mathematical explanation of matrix calculation of self-attention right here. Okay, so basically this self-attention, this is like a really naive and vanilla self-attention. It only projects the, you know, this kind of relationship or this kind of like encoding relationship into one subspace. What if we just want to project that into different subspace? So that comes with many heads, like many heads self-attention. So this is called a mechanism called multi-head attention. Okay, when you saw the word multi-headed attention, it basically means we don't do self-attention once. We actually do it many different times and try to project this specific word into, suppose, for example, suppose we have 3-head attention. And that basically means we try to encode this word into 3 different subspace over there. And previously, we just encode that into 1D or 1 dimension, but now we just want to project that into 3 dimension. So it actually improved the performance of self-attention into 2 ways. So the first kind of advantage of that is it expands the model's ability to actually focus on different positions. So for example, if you look at the example, right here, like we had right here on thinking machines. If we just use the self-attention, this actually has some kind of potential problems. The biggest problem could be we will always focus on thinking itself. Because thinking is thinking, it is itself. So if you try to figure out what's the relationship between thinking and thinking, it's always like gonna be close to 1. It's always gonna be 100%. So in that way, it actually doesn't really give you a process or give you some kind of like a lesson for the model to learn. So if we actually project thinking, or if we actually try to look into this word, encoding that into different perspectives, it's gonna actually, it's actually gonna solve that kind of problem. So specifically, that means, that one here contains a little bit of every other encoding, but it could be dominated by the actual word itself. It would be useful if we actually translating a sentence like the animal didn't cross the street because they were too tired. We would want to know which word it refers to, not only to itself, but we want to know which other words this one refers to. So if you just want to project this kind of encoding into 1D dimension, it's always gonna, project to itself. But so let me think how to actually explain this problem. Think about there's you're standing under the road road light. Okay, if the road light is actually projecting from the top of your head, it's gonna project yourself to yourself. You don't have a shadow. Think about it's like on top of your head. But if you actually use a different kind of road light, which is like, let me draw this. I think it should be look like this. Yeah. Okay. So suppose you're a person standing here, and suppose there's a light on your head, straight on your head, and the light is gonna project right here, right? It's gonna project yourself. So you don't really have a shadow because the shadow is under your feet. Then you and your shadow are actually most correlated because it is yourself and your shadow is just under you. So you can't separate yourself from the shadow. But what if we have different road lights? It's gonna look like you like that. Then your shadow is gonna be projected in this way. It's gonna be a little bit longer, right? And if we have another road lights projecting this way, your shadow is gonna be so much longer, okay? So in that way, I can isolate the shadow from yourself, not only not confusing yourself with the shadow. So think about this is word embedding. You're the word embedding. The shadow is actually, the score or the weighted value or how much focus we should put on yourself. Okay. So if you only project it into 1 dimension, so suppose this is 1 dimension, you can't actually distinguish yourself from the shadow. But if you project it into multiple dimensions over there, there are multiple ways of projecting the shadows. Then the shadows are separated from yourself. And also the shadows come with different lengths. So it means we basically have different understandings of itself, of yourself. Okay, does that make sense? That's why we have used like multi-head embedding over here. Any question with this part? I just want to, make sure you understand why we use multi-head, like from this perspective. Because we don't want to focus on yourself 100% of the time. We try to think about how to distinguish yourself from your focus, because we don't want to, focus always on yourself. Okay, so the second part is actually it gives the attention layer multiple representation subspace. Just like I mentioned previously, the multi-head attention not only have one, it has multiple sets of query, key, and value weighted matrix over here. So in that way, you're going to actually have different kind of score or softmax score of this kind of like specific word over here. So for example, suppose we have 8 different attention heads. The first 2 could like those 2. And we just do the same kind of procedure as we did here, okay? For each head of attention over there, or for each head set of query, key, and value vectors, and with their trained weights, then we get a different kind of, different kind of like a Z1 vector here and Z2 vector right here. Okay, so for 8 different attention head, we're going to have 8 different softmax score, or 8 different Z1 here. Okay, so it's going to give you 8 perspective of your shadow or yourself on the ground. Okay, so that's how that works. Okay, So yeah, basically that's a multi-head. So what if, suppose we have the multi-head attention, how do we actually use all of them? How do we actually, try to freeze that into feed-forward layer? Because the feed-forward layer doesn't actually accept multiple, like separate input like this. So we have to think about a way to actually concatenate or try to actually combine all those kind of like, Z vectors or the attention head vectors together. So one way to do that, just like before, just like how you actually generate a query key and value vectors, you have to think about, you have to generate a weighted matrix weight 0 and multiply and concate all the vectors and multiply the vectors by the weight here to reduce the dimension to generate a weighted, or yeah, you can think it's a weighted and multi-head vector in this way. Okay, so we concate the matrix and multiply them by additional weights matrix W0, and we get a Z matrix that captures the information from all the attention heads. Okay, so yeah, this is just like another graphical explanation of how we do the attention, self-attention over there. So basically, it's more general from the beginning to the end, which is what we already mentioned previously. I will just jump over that part. Okay, so now the interesting part is once you finish the self-attention, you can select how many attention heads you wanna project to, or the result from the multiple attention head over there. Suppose we only selected 2 attention heads, 0 and 1, and we try to look at for each attention head or for each attention vector, how much focus we should put on other words when we encoding 8 here. So one head actually says that we should actually put most of the focus on tire, and another head said we should put most of the focus on the animal. Okay, so see, if you use a multiple head, it gives you different understanding of how the 8 are correlated with the other words. So is 8 correlated with tired? For sure, because 8 refer to animal and 8 should be tired. Should 8 be correlated with the animal? For sure, because 8 is animal. So it gives you different kind of perspectives to think about how 8 are correlated with the other words over there. But if you actually put all the self-attention head, 8 self-attention head together, it'll be a little bit hard to interpret. It'll be very hard to interpret. So the solution is you need to think about which attention head is most important and select the most important attention head and use them. Okay, so that's basically everything about self-attention. Any questions so far?
And you can repeat your last sentence because you were cut off a little bit.
Oh, okay. So basically, if you put all the attention heads, try to figure out the linkage or how much focus we should put on other words when we encode 8. It's gonna be super hard to see because each attention head is just like each single person tells you should go here, you should go there, you should go to north, you should go to south. It's really hard to think about which way we should go. So the best solution is try to think about the most important attention head and only use those to figure out the linkage between the word 8 and the other words over there. Okay, so that's everything about self-attention. Any question about that part? Now, since we mentioned about self-attention, the reason for self-attention is basically when we try to encode a word, we try to think about how the words are related to other words. So this is just try to mimicking our brain's function. So think about when we read a paragraph, when we read a paragraph, we don't read each word, individually. We always think about the word, with respect to the previous bunch of words and with respect to the next part of the word. So you always think about the relative meaning of the word or relative position of that word in the paragraph. You don't actually isolate that word from the other word over there. Basically, that's the intuition behind the self-attention. Okay, so now coming to the positional encoding, which is a question just proposed by Yusa over there. So what is positional encoding and why do we need it? So one thing we actually haven't talked about is we always think about each single word right here, and we didn't really talk about the order of the word. We didn't really talk about, you know, how do we actually position each kind of word over there. So this is actually going to be a huge problem if we don't care about the order in the sentence over here. Because order actually tells us sometimes, it actually, not sometimes, 100% times, it actually tells us how to actually read the sentence and how to understand the, you know, the relative meaning between each kind of word over there. So the position also matters when you do the encoding. So just like I mentioned here, one thing we're missing from model is, you know, we have described so far is a way to account for the order of the words in the input sentence. We haven't talked about order. So to address that kind of problem, the transformer actually add a vector of each kind of embedding. Those vectors are actually called positional vector, and those vectors actually follow a specific pattern for the model to learn, and it helps to determine the position of each kind of word or the distance of different word in the sequence over there. Okay, or alternatively you can think about it as relative words position over there. Okay. So the intuitive here is actually try to add those kind of values to the embedding, and which is going to provide a meaningful distance between the embedding vectors once they are projected to the query, key, and value vectors. So how do we actually get, you know, the ordered embedding? So it's a combination of you know, two parts. One is embedding itself. Second is a positional encoding, which is a bunch of vectors have the same length of the embeddings, and it tells us which position je and suis and adjudant should be in the sentence over there. Okay, and we actually, you know, add those two together, and we actually generate the embedding with the time signal, or if it's a positional signal. Sometimes we call it the time signal or positional signal right here. So this is the output, the final output we are going to put into the bottom left encoder right here. Okay, so it actually looks like this. So this is positional encoding. That's the embedding. You add those two together. So don't try to understand what that means, each kind of number means in the positional encoding, because those kind of words are not generated randomly. With respect to how to actually generate a positional encoding, I don't have a specific answer right here because it's going to be a longer story, very long story. So I suggest you guys go back to the paper and try to look at how the positional encoding are actually generated over there. But my understanding, like, don't get trapped by those kind of number right here. Don't try to think about what specific meaning each number inside positional encoding represents. It's not that important. The important part should be how do you actually come up with those words right here. Okay. So this is another way of represent the positional encoding right here. Okay. So now we actually combine those two different parts together. We have already known the order of the words, and we already know how this kind of each specific word are related to other words over there. So next part is, what if I just want to jump over some kind of layers in the encoder and just pass the input to the next layer directly? So to actually avoid vanishing gradient problem, or try to actually use the input directly. So that comes with another structure of the encoder, which is the residual, or sometimes a more specific neural network is called a ResNet, residual net over there. Okay, so one tail in the architecture of the encoder is that we need to mention before I move on, is that each sublayer sometimes, or most of the time actually, in each encoder it has a residual connection around it. So it is followed by a layer normalization step. So basically, what we mean is, when we do the self-attention, before we do self-attention, we could pass the two words directly to the normalized or a normalization can layer, and then forward those two words into the feed-forward neural network over there. So that is, we don't want to lose some kind of information from the original words after self-attention, but we also want a self-attention. So why not just pass those directly to the normalized layer, then actually feed it to the forward neural network, plus the output from the self-attention over there. Okay, so this is like really similar to the vanishing gradient. So basically, we try to actually capture as many information as we can from the original sentence over there. Okay, this is not, yeah, basically that's a more specific, like explanation. Basically, as you can see here, we have 2 words and 2 embeddings. Before we feed it to self-attention, it's gonna x1, x2. So we pass that into a normalization layer with x, original x, but we also pass the self-attention output that into the normalization layer. Then we normalize the summation of the 2 or the concatenation of the 2. Then we pass that into a feed-forward neural network. So in that way, we not only capture the relationship between this word and any other specific word, but also the original position of each word in the original sentence over there. Okay, that's the encoding. For the decoder side, there isn't a lot of there aren't too much to actually to talk about, because it's pretty much very similar to the encoding. But one kind of like a difference between the 2 is, like I mentioned previously, is the encoder-decoder attention. Okay, so the encoder starts by processing the input sentence, the output of the top encoder. So just like this. Once you finish that, you put those 2 into the encoder and decoder again, and it's gonna generate the first output over there. So the output of the top encoder is then transformed into a set of attention vectors, key and v over there. Okay, so it's going to be transformed into a key and v vector over here. And those are going to be used for each decoder in the encoder-decoder attention layer, which help to decode focus on appropriate like places in the input sequence over here. So this graph shows you how the whole process is going to work. Okay, that's this decoding part. Yeah, this is more like a general like encoding and decoding process. Not only, this is just like a single word. What if we have multiple words? So it's gonna work like this. So after step 6, let's go back to the original one. Yeah, so once you finish this first step, then you're gonna decode again using second word, decode again, get another word, so on and so forth. So basically, you're kind of repeating the whole process here many times until you get the end of the sentence over here. Okay, so the following step repeat the process in former encoder output over here. The output of each step is fed to the bottom decoder in next some step, and then the decoder is going to bubble up or stack up their encoding result, just like the encoder did, and in decoder again, until at the end you generate the corresponding word using all the previous word we have. Okay, so this is unidirectional decoder. Basically, every subsequent word decoded is going to be based on the previous word over there. Okay. Yeah, I will just jump over the softmax and the linear layer, because we already know that softmax is actually try to calculate the possibility of each word appearing in this sentence over here. So that's not that important over there. The loss function. Okay, so the loss function. So see, we are training our model. See, it's our first step in the training phrase, and we are training it on a simple, simple example, translating max C to thanks. So what this means basically is that we want, in the original kind of sentence over here, we want actually thanks to have 100% possibility to show up in the sentence, because that's a word we are translating to. Then in the train, output over there, we should have a max C that actually also have the highest possibility in the sentence over there. Okay, so generally speaking, for example, suppose we try to translate the French "je suis étudiant," I'm a student, into I am a student. So in the target model output, it should look like this. So if we try to look into I, we try to translate the into I, then I in the target center should be have 100%, like a possibility. So the distribution should look like this. And if we just look at the word M, then the distribution should look like this. If it's a word A, it should look like this, so on and so forth. So in the training model outputs, suppose we train each kind of word over there and we concatenate them together as our distribution graph like this, then I should be close to 1 so that we know that I should be translated to this word here in French, which is je over there. And M, which is 3, should be like also close to 1, just like the position should look like this, which is 80% here, which is quite close to 100% right here, and so on and so forth. So when you translate a whole kind of like set of words or the sentence or the sequence of the word, it's not like a vector of each single word as a possibility. It's actually a 0, 1, 0, 1 kind of vector. So each one word has its own kind of distribution, and you stack all those together and you compare those two distributions and try to look at which one is closer to the target distribution over there. Okay. So basically this one is doing a pretty good job. As you can see, all the numbers are in the right position and their distribution are quite kind of close to 1, or their possibility quite close to 1 as well. Okay. Okay, that's basically everything about transformer. Any questions so far?
Hi, Daniel, I have a question.
Sure, yeah.
I think the paper says transformers is parallelable, like can be computed in parallel. So how this parallelism works in this way?
Sorry, can you say it again? So it can be computed what?
Parallel.
It can be computed in a parallel way.
Yeah.
Oh, my understanding is that it's parallel in this way. Those two, I guess. So I think there's a specific sentence like, give me a second. I think there's a specific graph telling about dependency. Oh, yeah. So here's how we begin to see one key property of the transformer, which is that a word in each position flows into its own path in the encoder. There are dependencies between these paths in the self-attention layer, but the feed-forward layer does not have those dependencies. Basically, the feed-forward neural network are independent to each other. They're kind of going in a parallel way. And however, that's whereas like paths can be executed in a parallel while flowing through the feed-forward layer. Yeah, I guess the parallel actually refers to the two kind of like neural network, feed-forward neural network are actually implemented parallelly for different kind of word in the sentence over there.
So the next word has to be dependent on the previous word in this way.
Only in the feed-forward neural network layer. Because you don't need that. Why? Because this one is not a word itself. This one already contains the relationship between that word and that word. That one
by using the self-attention.
Exactly. Yes, it already has a the relationship between this word and every other word. So why do we actually why do we care about this part? We don't actually need the whole free neural network anymore. We can just run them separately.
So this is the only part that can be computing in parallel.
Yeah, in a vanilla, in a really naive transformer, yes.
Okay, cool.
Yeah. Good question, yes. Any other questions about transformers? Okay. If you got time, I strongly suggest you to actually give it a read of this kind of blog right here. I think this is pretty straightforward, and also this is also the officially recommended like post by the lecturer, Professor Michael Manning, Chris Manning. Actually, he actually recommended a lot of posts by G. Alamber. He is really he's like a genius. He actually try to understand all those kind of concepts from a really straightforward way, and has many posts that try to explain those complicated models in a simple way. So I strongly suggest you guys to look into his post, especially this post right here about transformer. So next part, let's talk about finally, what is BERT and what's the relationship between BERT and Elmo and Operation AI or Open AI, which actually mentioned by Ray previously. So I'm gonna okay. So first, I'm gonna tell you guys how BERT can be used too. So BERT is BERT stands for Bi-Directional Encoder representation from the transformers. It's basically a bunch of the transformer encoders stacked together. Not the whole transformer architecture. Basically, we only use the encoder. Okay. So the concept of the bidirectionality is the key differentiator between BERT and its procedures. Later on, I will tell you how amazing this bidirectionality is going to be. It's just a super genius, like a way to actually try to think about the relationship between each single word or each piece of a text from the previous part of the text and subsequent part of the text. And its procedures, OpenAI GPT. BERT is bidirectional because its self-attention layer performs self-attention on both directions. So just keep that in mind for a second. So the key part is that BERT actually performs self-attention on both directions. But previously, if we just look at a transformer, self-attention is actually performed one direction. It's actually performed one direction over there, because especially for the decoding part. Where is that? For decoding part, where is that? For decoding part, especially for the decoding part, basically what you do over there is you actually try to predict the next word based on the previous word. It's like a one direction over there. But for the BERT, it's actually bidirectional. I do not only read the word from left to right, but also from right to left, which I'll show you later. Okay, so basically that's the definition of the BERT. So BERT think about BERT as the contextual words representation. Basically, it's only referred to the encoding part. That is, after the encoding, we have the two vectors, which is representation of the input sequences we have. Or you can think about it as contextual word embedding. It's contextual word embedding, which refers to the position or the contextual meaning of each kind of word using a bunch of like a matrix over there. Model, model, it's like just embedding. Okay, so since it's some kind of embedding, what can it be used for? Another amazing part of BERT is that it can be used for many different natural language processing tasks. It can be used for classification. Once you have the word embedding, you can feed that into a classification neural network and trying to classify whether it's a spam or not spam. Or it could be used for question answering, or it could be used for other different kind of different kind of tasks over there. So specifically, it can be used for sentiment analysis. So try to see whether the product or movie preview is positive or negative, or it can be used for fact checking, or ambiguous futuristic example is going to be a claim sentence. Basically, you just give the model a sentence, or give the model a bunch of like a Twitter from Donald Trump. It's going to figure out what's a claim, what's the center idea of this kind of tweet over here. So one example is that full fact. Full fact is actually organization building automatic fact checking tools for the benefit of the public. Part of their pipeline is actually a classification model that reads news articles and detect claims. And the center kind of like model they use here is actually BERT. Okay, so if you want to actually learn a little bit more about the potential, application of BERT, you can actually click the link right here and try to see how those are or the source codes add those application of the BERT right here. So now let's talk about the model architecture. So the model basically have two different kind of like model sizes for BERT base and BERT large. BERT base actually comparable in the size to OpenAI transformer, which I'll talk about later, in order to compare performance. And BERT large, usually I haven't seen anyone using BERT large except for the original paper. It's a ridiculously huge model, which has 24 transformer encoders achieved to the state-of-the-art results reported in paper. Okay, so this is BERT base. It has 12 encoders, and BERT large has 24 encoders, and it could have billions of like can dimensions and also parameters, especially for the weights. It could be like a huge like a weight over here for you to generate the key value vectors over there. Okay, so the model inside the model, the architecture is pretty much the same. So it's a bunch of like encoder just like before. Okay, so basically you just input a bunch of like a different word over here to actually through the self-attention layer and feed forward neural network. So going back to the post here, it says a dual self-attention layer performs self-attention on both directions. So previously the self-attention layer for the transformer only goes one direction. Why? Because when you input the word into the sentence over here, you put the je suis first, je for 3 seconds, and you don't third. So if you don't have the third word, if you don't put the third word here, the first word or je can only do the self-attention on the second word, not the third word. Okay, so if you actually suppose you actually put all this kind of like, suppose you don't put a third word over here again, you only do the the self-attention with je on suis over there. Okay, so it doesn't actually go to another direction. It's not like you go you can just do suis on je again. So you already do like self-attention from left to right. You cannot actually going back to the suis to the je, or you cannot actually go into the next. You can actually not go into the next direction. So to be more specific, think about the example. Suppose we don't have the adjudant. One direction could be je to the suis. So that's a self-attention to je to itself and je to the suis here. And when we go to the next word, it could only go one direction, which is this direction, suis to the je and suis to itself. Okay, so see, both words can only go one direction. It can actually not go to another direction. It's actually unidirection. But BERT actually try to do the self-attention by using all different directions. So basically, it's going to give you the full sentence. It's going to not give you the words word by word from left to right. I'm going to give you the full sentence. Then you can actually try to figure out self-attention between this word and the previous word and all the afterwards. Okay, which I'll show you later how BERT can actually do that for the bi-directionality. So other than that, it's pretty much similar. It's very similar to the transformer encoder. So nothing too special for the encoding stack part right here. Okay, so okay, I don't think there's any specific stuff I want to talk about right here. Okay, one more stuff is depends on the task you want the BERT to do. Sometimes if you want actually the encoding or the transformer to do a classification later, which like this. So if you just want to do a classification after you finish the BERT, then basically in the first token, you have to label that as the CLS. So the first input token is supplied with special CLS token, which is classification token. For reason that become apparent later on the classification here, stands for classification. Because if you actually label that with CLS, later on, the machine gonna recognize that as a classification task. It's gonna use a BERT for the classification of the word embeddings you generated from the BERT. Embedding. Okay, Elmo. Before we actually go into BERT, I'm going to talk about the previous two models, and those two models are actually the main motivation for BERT. So one of the model is called Elmo. So Elmo, I won't go to too much details over here, but Elmo is also embedding or contextual, word embedding techniques. So the main framework of Elmo is bidirectional LSTM. Okay, basically, you go one direction using the previous word from left to right to predict the next word, and then you concate that to the next layer, from another direction, from two to the stick to the left, to the left. Basically, it's a two-direction or bidirectional LSTM, just like before. It's more like a language model. So basically, its task is try to predict what's the next word going to be, using two directions, using the previous text and using the next part of text. For example, if we try to predict the stick right here, one direction could be I use less to predict the stick. Another direction could be use a two to predict the stick. So basically, the advantage of Elmo is that I use all the context to predict the center word or any specific word, not just one direction, both directions, so that I can capture the previous context and the subsequent context. Okay. So that's the Elmo right here. Yeah, so basically this is, the full look of the Elmo. This is, from left to right, right forward LSTM. This is left forward or backward language model or LSTM. Basically, you compute those two models together, then you get an Elmo, which is, the theoretical foundation for the Elmo embeddings. Another model, which is called Ulim fit here. So Ulim fit is another model which is a specific or application of a transformer. I won't spend too much time on that because this is not really the center of or the theoretical motivation for the BERT. So I would just jump to the OpenAI transformer. So this is another model aside from Elmo, which actually motivates the BERT. So OpenAI transformer is a specific part of or specific form of transformer, which is the pre-training of transformer decoder for language modeling. Okay, so basically, this model is more like just using the decoder from the transformer and try to predict the next word using the previous word. It's a unidirection. Okay, so it turns out we don't need actually the entire transformer to adopt the transfer learning and fine-tunable language model for natural language processing. Because for language model, we just need the previous word embeddings. Then we just use that to predict the next word. So decoder actually does this kind of job perfectly for the NLP task. So we don't really need the whole transformer task. We just need a decoder from the transformer. We can do this with just a decoder of the transformer. The decoder is actually a pretty nice choice because it's a natural choice for language modeling, predicting the next word, because that's what decoder do. What is just predict the next word using the previous word. Okay, so if your goal with the OpenAI transformer is to do a language model, then the decoder is enough. The model stack 12 decoder layers. Since there's no encoder in this setup, the decoder layers would not have encoder-decoder attention sublayer. So it only have the self-attention layer and feed-forward neural network. It will still have the self-attention layer, however, just like I mentioned right here. So with this structure, we can actually train the model on a same language modeling task, predict the next word using massive previous words. And throw, for example, we can throw the textbook of 7,000 word, a text of 7,000 books right here into this kind of model. It can actually use every single word in the previous context to predict the next word over there. Okay, so one question here is, if we actually look at OpenAI transformer, is this transformer unidirectional or bidirectional?
I think it's unidirection.
It's a unidirection. That's totally correct. So OpenAI transformer can do the language model for you because they only use a decoder from the transformer, but it's unidirection. It's not bidirection. So that actually motivates BERT. Can we actually combine Elmo to OpenAI transformer to do a bidirectional transformer? not only using the previous context, but also using the subsequent context and try to wrap the word with the context around the word, try to understand the relationship between the word and every single other word. Then we can use that contextual embedding to do other tasks over there. Okay, so the OpenAI transformer gave us fine-tunable prediction model based on the transformer. But something went missing here from the Bi-Lstm, from the Elmo model to the transformer. Elmo language model, it is bi-directional, but OpenAI is a forward language model. It's unidirectional. So could we actually build a transformer model, actually combine those two together? Use both left to the right, like a LSTM, but also the, the OpenAI transformer? The answer is yes. So here comes another question. Why not just apply, why not just, add encoder to the OpenAI transformer, let this transformer to do bi-directional kind of like, work. That is, for example, the question could be, can we actually do the bi-directional encoders in the naive or vanilla transformer? Can we actually, do the bi-directional encoding here for the naive traditional transformer? I said we can. I said we can previously, but why? So the reason is, if we try to do the bi-directional, encoding in the traditional transformer, that is, we try to perform a bi-directional self-attention, then the model would learn what the next word is in the sentence in the target and would predict always with 100% accuracy. Okay, what does that mean? Basically, if we do bidirectional, if suppose we put all the context here, we put the Je suis étudiant right here, and the model already know the next word after je is suis, then it's gonna do the self-attention with that 100%. Then it's like you already leaks the answer to the model. The model knows what the answer is. Of course, it will predict the next word as suis corresponding to am. Then what's the point of using this? What's the point of doing encoding bidirectionally? Basically, you are cheating on yourself, like, letting the model know what's the next word going to be. Of course, after the self-attention, it's going to, link that word specific to that word with 100%. After, long time training, later after layer, and other words going to be 0% linked to this specific word right here. So we can't do bidirectional, I would say self-attention and also encoding in a traditional transformer. So that's why, we need another kind of like a transformer that can help us do this kind of job. But how do we actually tackle that problem? How do we actually let the model learn what's the next word going to be, or what's the previous word going to be, or what's the surrounding word going to be, without leaking the answer to the encoder, to the transformer? So that's a smart one, kind of a genius innovation from the BERT. So BERT actually, just like I mentioned, is a bidirectional encoder representation from the transformer. So how do we actually interpret the bidirectional? So it actually, does like two different tasks. Try to actually not leak the answer to the model, but also let the model learn what the answer should be. So that one of the tasks is actually the mask task. So basically, in the model, for the input sentence over here, 50% of the words is going to be masked with mask token. So what a mask token is, think about it as a facial mask put on the word. The word has been hid away from the model. The model cannot see the word anymore. So basically, for example, let's stick to improvisation in this gate right here. Okay, so I'm gonna mask improvisation here. So if we actually mask that, then the input center gonna look like this. We don't really have that word anymore, right? We don't really have that word anymore. We're gonna put that into the BERT, into the encoding, And the encoding is gonna be responsible for predicting what this word is by using self-attention from that mask token to all the previous and all the afterwards, afterwards kind of like after subsequent words over there. Okay, so that's a smart part of the BERT. I'm not leaking the answer to you. I'm going to cover the answer to you, but I'm going to give you the contextual or other words surrounding the word, and you're going to predict what's the word going to be in this position. Okay, in this position. And after the BERT transformer, after encoding, after self-attention, it's going to tell you what's the relationship between this mask token with respect to other kind of like word over there, right? And based on those kind of relationship, it's going to predict what this word is going to be. And we're going to compare the predicted word to the real word and generate the loss function and trying to minimize the loss function over there. So that is, we are going to use the target. We're going to use that as a true label. This is a fake label. And we just give the model the fake label and try to predict the true label right here of the word. Okay. So that's the one kind of like a really, really genius like innovation of the BERT as a potential like a transformer encoders over there. Does that make sense to you guys? Okay, so that's the difference between the BERT and transformer. I don't actually give you the word. I just cover the word, and you're going to tell me what that word is. So in that way, the answer is not leaked to the model. So the model can actually use the self-attention of that word with respect to all direction kind of word to actually predict what that word is going to be. So that's one kind of task the BERT is going to do, but that's not the end of the story. I mean, even though you predict a word and the model said, oh, let's stick to changes in this kind of skate. Suppose I predict the word changes, right? It's kind of like a similar to improvisation, but it's like a neutral word. It's not like a positive word. So how do we actually judge whether it's right or not? Or how do we actually judge whether this sentence makes sense or not? So another kind of task to solve that problem is we have to make sure the sentence actually fit into the entire article or documents, like according to the previous context and next context. So for example, the previous context could be, oh, we actually lost $500 million last year. Let's stick to improvisation in this skate right here, right? So the next task, which is called two sentence task, is going to make sure this sentence is actually after that sentence, is actually in the right position in the document over there. So we do not only care about within the sentence the word is correct, but we also want to make sure the sentence itself is correct with respect to the entire document over there. So if you look back up at the encoder transformers and OpenAI transformers, who actually just handle the different tasks, you're thinking about some tasks require the model to say something intelligent about two sentences over there. Okay, so to make BERT like a better at the training process also including additional time, which is we give the two sentences to the BERT model, then the model is going to tell us is B likely to be the sentence that follows A or not. Okay, so for example, this is sentence B, and we also give the model another sentence A. Then this model is going to compare, the sentence B and the sentence A, and going to see how much similar those two sentences are with respect to B to another sentence over there. So suppose this is sentence A, that's a sentence B. So the goal is try to figure out or let the model learn that sentence B should be follow sentence A. So I remember the model does, the paper actually mentioned how we actually performed that is that we actually change the sentence A with 50% right sentence, 50% wrong sentence. Then we actually train the model and comparing this sentence with all the previous sentence over there and try to see those two sentences can be linked together or not using self-attention over there. Okay, so I think there's specific details over there here. So if you are interested into how the model are trained specifically, like the two tasks, which is mask task or mask language model here, and another task would be the two sentence or next sentence prediction task here. So this link here, which is understanding BERT part 2, I think it's right here. Third link right here is where you can go to actually find more specific details over here. But the general understanding is like for sentence task over there is 50% of sentences were paired with the actual adjacent sentence in the corpus, and 50% of them are paired with randomly picked the wrong sentence over there. Then the model gonna compare which one is the right sentence to follow over there. And for the mask task over here is 80% of the word are replaced, 50% of words are replaced with mask, but 80% of the mask are replaced with mask token, and 10% of the masks are replaced with a random token, and 10% of left, just the original right word. So this is actually let the model learn, at least there's some kind of right model, right kind of like a word to actually predict to. Otherwise, if you replace them with all wrong kind of words over there, the model doesn't really know which kind of word to look up to for the right direction over there, okay? So in that way, we can, using a mask, we can actually do the bi-directional encoding or bi-directional self-attention. But without a mask, it's really hard to do so. Just like I mentioned previously, without a mask, you are leaking the answer to the model, then the model is actually learning nothing because you already tell the model what's the next word going to be using the encoding, or tells the model which word we should focus on when we're encoding a specific word over there, okay? All right, that's pretty much everything about transformers and BERT over here. Any questions so far?
No, I think so. So Daniel, for the resources you shared, I think. Do you think how much time will each of those gonna take? Because I think if we dig into details of the BERT, I think we probably need to learn separate things.
Yeah, it depends like what you really actually want from the BERT. If you really try to understand, try to use BERT like empirically, I strongly suggest that you finish those two readings, Illustrate Transformer, Illustrate BERT first, then go to the visual guide to using BERT for the first time. This post right here, which is by the same person, and he actually shows you how to do those using specific numbers. And also, the most amazing part is the code. Okay, so if you try to understand how BERT performs, in terms of coding, you can just look into this kind of post right here. But if you want to know more theoretical foundation, I strongly suggest you go back to original paper. It has super like detailed explanation over there. But if your goal is try to understand a model, just try to know what a BERT is, just generally speaking what a BERT is, then the two link right here, Illustrator Transformer, Illustrator BERT, should be okay. And I spent pretty much 3 hours, 4 hours on the two, on the two kind of link right here and trying to understand each concept over here. Yeah, I think you can pretty much finish all the posts like within 3 hours, 4 hours, I guess.
Sounds good. Thank you.
Yeah.
Yeah, I'm thinking like we already have the pre-trained word embeddings. So when we were using this to fine tuning on our like later specific tasks, so how are we gonna exactly like implement that? So I am thinking just using this embeddings as a I don't know how to say that. So
I really don't know the answer for that part because I haven't done any kind of project on that. But my guess is that you can use a word embedding just like a word-to-vec embedding or globe embedding to represent a word as like an input for each kind of single word. Suppose you try to do a movie preview kind of like classification. Suppose I really hate this movie. Then you already have the word embedding for I hate this movie, all the words right here. Then you just replace all the words and using the word embedding through some kind of library. You feed those kind of embeddings into the classification model and try to predict whether this sentence is positive or negative over there. That's my guess, but it could be more complicated. But more specific details, I think you can find it right here in this BERT notebook right here, I guess.
Cool.
Yeah.
I think it is worth like trying.
Yeah, it should be, yeah. Yeah, I guess the most important takeaway is like, if people ask you, can you do bidirectional, self-attention in a transformer, within a transformer, the answer should be no. There's no way you can do that, because that would be super stupid. Because just like I mentioned previously, if the interviewer asks you so, you should say no. Why? Because we don't want to leak the answer to the model. That is, previously. So this is a really bad example by the way. The 8 here should be always like, do the self-attention to the previous word, not after word over there. Because otherwise it will already know the target word. Suppose, those words are the target word, then you shouldn't do the self-attention with 8 always all the target word over there. So you should always do the self-attention with 8 and all the previous word. But suppose these 3 words, the animal didn't are the target word, then you should do 8 with other words, not these 3 words over here. Just like when you do the classification model or the regression over there, you don't want to leak the test set to the model, then do the test set classification, because you already, like the model already know what the test data is, then it will give you 100 accuracy on that. So self-attention is the same. If you try to predict a word that has, that's a target word or 100% link with the word that you have, then you shouldn't leak the word to the encoder. Otherwise, already know what the word is. Of course, it will just give you 100% like a linkage to that. So the one way to do that, like if the interview going as follows, how do we solve that problem? We can use BERT. Why do we use BERT? Because we covered that kind of like a task, like a target word with a mask. It's not linked to the model, so the model have to use all the subsequent on the previous word, try to predict what that word is. So for example, it's very similar, super similar to the way we read the article. For example, suppose I want a jacket. Suppose here, mask, because it is damaged. And I just suppose this is a sentence you just said as a customer to the sales girls. What do you think the mask is going to be? So let's give you several options. Throw, just one word. Pretend that's just a one word. B, return. C, keep. Which one do you think like we should put over here for a mask over here?
Return.
Return. How do you get a return? How do you know it's a return?
From the context that is saying it's damaged and
we just bought it last week, right? Exactly. That's how you understand how you actually predict return. That's how the model predict return. Bidirectional. See? So when you try to understand a word, you do not only think about the previous word, I want to, and this should be a verb. We also look at, all the subsequent word. Oh, it's damaged. And I bought it last week. Oh, so this one should be returned. This is how BERT works. BERT look at all the previous word, try to link the mask with all the previous word, and link this mask with all the subsequent word, and try to find the key linkage, which is damage, right? This could be a key linkage. Bought it last week, right? So those 3 keywords here, and 2, I want, defines what that word is. That's why we use self-attention, because self-attention tells you how to read the word or how to predict a word using all the previous information and subsequent information. Okay, that's the intuition behind a BERT. Okay. All right, any other questions? If you guys don't have any questions, we can just finish the lecture right here. Let's call it a day, and see you guys next week.
Thank you.
Thank you, guys.
Thank you, guys. Okay, talk to you guys later.